Welcome to Chemistry at Hononegah High School. Today we'll be looking at our first set of notes from Chapter 19, dealing with acids and bases. One of the things you should understand is a working knowledge of the properties of acids and bases. Now, one terrible way to tell if you don't know what it is, whether it's acidic or basic, is to taste it, because acids will always have a sour flavor. It deals with how they interact with your taste buds, which isn't a good idea if it's a dangerous acid, but many foods have a sour flavor to them, and especially when paired with sweet, it's actually a pleasant flavor for most people. So lots of cooking is actually playing with pH to make sure that it stays in the acidic range, because if it becomes basic, it becomes bitter tasting. And unlike sour, which isn't necessarily a bad flavor, bitter is really never a good flavor. Another terrible way to mysteriously test an acid would be to pour it on your hand. If after a short period of time it burns terribly, then it's probably an acid. And bases are a little bit quieter. Bases, on the other hand, by the time it starts to hurt, it's already done quite a bit of damage to the skin, at least with most acids. That burning sensation will quickly disappear when you get it diluted immediately with distilled water or with any type of water source. So often it may burn, but like in the lab, you spill a little bit, you feel a little burning sensation, you rinse it in the sink for 20 or 30 seconds, and it completely disappears. Well, in a base, if that were to happen, by the time it starts to hurt, it's actually done significant damage to the proteins in your skin. Whereas at the very beginning, when it's just starting to cause problems, it'll feel slippery. So if you got bleach on your hands, that's a basic substance, and that'll end up feeling slippery. Well, that's the liquefaction of the dead skin cells and freeing up the oils on the outer surface of your body, which isn't a good thing, but honestly, your body has barriers to prevent that from doing too much damage as long as it's not there for too long. But it doesn't burn right away like an acid would. Now, another way to test safely whether something is acid would to be put it with a reactive metal to see if it makes bubbles, and if those bubbles are hydrogen gas, because acids will do that and bases will not react with reactive metals to make hydrogen. One of the things that is not a difference between acids and bases, but it's a property they share in common, is both acids and bases are electrolytes. You put them in water, they'll make water conduct electricity. Now, sometimes you'll be looking at the formula of a substance and you'll be asked whether it's an acid or base. Well, we typically start the writing of acids by putting a hydrogen, because acids will typically have ionizable hydrogen in them. So you'll often see when writing an acid, you'll see a hydrogen right at the beginning of a formula. So the formulas of acids usually start with a hydrogen. And bases often have hydroxide. So at the end of the formula, because that's an ion, or an anion, we'd put anion second, you would usually see OH at the end. So that's a quick clue sometimes you got an acid or base. Does it start with hydrogen, acid? Does it end with hydroxide, base? And remember, water is true neutral. Well, it's got an H and an OH. One of each. They're equal to each other. Now, one of the ways in the lab that we typically will use to tell acids from bases is to use chemical indicators. There are chemicals that have an acid color and a base color. A good example would be something like litmus, because litmus is a non-toxic, perfectly safe chemical. And blue litmus paper is litmus absorbed on the surface of paper in its slightly basic form. So if you have blue litmus and you put it in an acid, it will make it turn red. Red is the base form of litmus. So if you have litmus absorbed on paper and it's in a slightly acidic environment, it will start out red. We'll put it in a base and it will turn blue. So the best way to tell if you got an acid or base is to use red and blue litmus paper side by side. If you put them in an acid, they'll both end up red. If you put them in a base, they'll both end up blue. And if they keep their original colors, that meant you were putting them in a neutral solution. So that would be a safe way to quickly test if something was an acid or a base. Or in water, is it making the water acidic or basic? Another chemical would be phenolphthalein. It's another non-toxic chemical. One of phenolphthalein's original use was actually as a laxative. In its base form, it is red to pink, and in its acid form, it's clear and colorless. So if phenolphthalein is red and it turns to a clear colorless color, then you now have an acidic solution. And if you have a acidic solution, it'll be clear and colorless. Add a base until it turns pink, and that tells you now it is basic in nature. So phenolphthalein and litmus are two indicators that we can use to test whether something is acidic or basic. Now, what really makes an acid when you throw it in water make the water acidic, or bases when you throw them in water make the water basic? It deals with an equilibrium reaction, which is why we talk about equilibrium before we get to acids and bases, and it deals with the autoionization of water. Water molecules can break apart into H plus and OH minus. Now, when one water breaks, you get one H plus and one OH minus. If 100 broke apart, you get 100 H pluses and 100 OH minuses. So in a true neutral solution, those two concentrations are always going to be equal to each other. Now, water only does this to a very small degree. So if you had a billion water molecules, like one of them would break apart. But remember, water molecules are very small, like all particles. So when you have a glass of water, you have many, 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 many billions of molecules. So you will have some H plus and OH minus. But in a true neutral solution, the H plus will equal the OH minus. Now, anytime that you end up with H plus greater than OH minus, and this is really an equilibrium situation that we talked about last chapter, if we add an acid that like HCl, which contributes H plus, that's going to make this concentration go up, which, as we talked about by Le Chatelier's principle, is going to increase the reverse rate, which is going to shift equilibrium to the left, which fundamentally means we're going to start using up H plus and OH minus, so that's going to drive down our OH minus concentration. So literally by adding an acid into water that contributes H plus, it's going to make H plus go up and OH minus go down. So anytime we have more H plus than OH minus in a water solution, then we call that acidic. Acids would be things that do that when we throw them in water. What do bases do? Well, they do the exact opposite. Bases would be typically things that dump OH minus into water. Once again, doing the same thing. Shifts equilibrium to the left, which means H plus concentration is going to end up going down. And therefore, in a basic solution, OH minus is greater than H plus. So remember, in neutral, they're equal. But when we put things that make water acidic or basic in water, they play with the neutrality, the equality of those two ion concentrations. Anything that makes H plus more than OH minus will make the water acidic. Anything that makes OH minus more than H plus will make the water basic. Now, terminology things that you need to be aware of as we start talking about acids and bases and different ways of identifying them. Whenever I talk about the hydrogen ion, which is interchangeable with the word proton, because a hydrogen atom in its normal form has one proton, one electron, no neutrons. So if we take the electron away and we end up with H plus, what we really have as the hydrogen ion is really just a proton. That's all it is. It's a strip nucleus with just a proton. That's all we've got. So the hydrogen ion is often referred to as a proton because they're interchangeable with each other. Now, H plus when in water doesn't stay H plus. It actually attaches to water molecules, making what's called the hydronium ion, H3O plus. So every H plus in water really exists as an H3O plus complex, the hydronium ion. There really isn't any H plus on a particle level when you look inside water. What it's really done is stuck to water and made H3O plus. So we use these two things interchangeably with each other. I know technically they're just a little bit different, but we refer to them basically as the same thing. So the hydrogen ion and the hydronium ion is really how the hydrogen ion exists in a water solution. So it's a hydrated H plus ion. And it's how H plus exists in water exclusively. So it really means fundamentally the same thing as an H plus. Now, bases, we often talk about hydroxide. That's OH minus. And we don't have a hydrated form of OH minus that we discuss. Now, our original model of acids and bases started with a scientist by the name of Arrhenius. And back in 1887, he said that compounds that ionize to make hydrogen ions, or protons, would be things that are acids. So if you have something like HCl, that has one ionizable hydrogen, so that's a monoprotic acid. Whereas something like H2SO4, sulfuric acid, has two hydrogens. It's got two hydrogen ions it could donate to water. It's a diprotic acid. So acids are things with hydrogen ions that they can contribute to water. And there are rare, but something like phosphoric acid, H3PO4, actually has 3 protons that it could donate. So it's a triprotic acid. Now on our base side, Arrhenius said that compounds that ionize to make OH minus are bases. So metal hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide, magnesium hydroxide, all of those things are basic in water because they have ionizable hydrogen. Now technically we could use mono and di to talk about how many hydroxides there are, but that's really something we don't do in first year chem. And the Arrhenius definition is nice because it's very easy. Start with hydrogen, you're probably an acid, and with hydroxides, you're a base, but it's fairly limited. Some things act like acids and bases without having an H plus or an OH minus in them. So there would be other theories that come along that are a little bit more general. Now, the Bronsted-Lowry model in 1923 was a model that two scientists working independently came up with essentially the same idea, so we name it after both of them. And what they were looking at is how they behave when you throw them in water or with other substances. So an acid would be a thing that is a proton or a hydrogen ion donor. So when you throw it in water, it's going to give a hydrogen ion to water. Kind of like what Arrhenius dealt with, but you'll see it's a little bit more versatile and can apply to more situations. So in this case, if we have HX, a general formula for an acid, we throw it in water, you see it makes H3O plus and X minus. What really happened here was the hydrogen from the HX went to the water. So HX would be an acid because it donated that proton to the water in the course of this reaction. Now a base, on the other hand, is a proton or hydrogen ion acceptor. The thing that gets the hydrogen ion is the base. And this is where this gets a little bit different from what we talked about with Arrhenius. Because in the Arrhenius, we wouldn't call water a base. It's water, it's neutral. But what Bronsted-Lowry is saying is, in this case, it's acting like an acid. That doesn't mean when we throw water in water, it makes the water basic. It's just with this acid, it's functioning like a base. Now, that would explain something like ammonia, which is a very common base, but ammonia doesn't have hydroxide. So how is it that ammonia is a base? Well, look at what happens when you throw ammonia in water. A hydrogen leaves the water, so now H2O is acting like an acid, and goes to the NH3 to make NH4+. You have to look at what it becomes to really see what's happening. That's becoming that, and that's becoming that. So clearly water was giving the proton, the hydrogen ion, to the NH3 because water became OH minus. It lost an H plus, and NH3 was gaining the proton because it became NH4 plus. So in the forward reaction, a hydrogen ion or proton leaves the water, that's why water is an acid, and combines with NH3 to make NH4 plus, making NH3 the base. And therefore water is acting like an acid here. So you can see that what really happened is it ended up making OH minus when you put it in water. That's why ammonia is a base. It did end up making OH minus in water. Now, one of the things of Bronsted-Lowry theory is when we have a double arrow, the reverse reaction is also occurring, and the substances on the right are conjugates of the substances on the left. But now they're acting differently. NH4 plus is going back to make NH3, and OH minus is going back to make H2O. So in the reverse direction, NH4 plus is donating the proton, H plus, to the OH minus. So NH4 plus is the conjugate acid of the base NH3, and OH minus is the conjugate base of the acid H2O. If you've done this right, you'll notice that the substance and its conjugate are always opposite of each other. So when we've got a double arrow, we also have acids and bases on the product side, and we call them conjugate acids and bases because they're literally conjugates of the substances on the left. And notice they come in pairs, opposite pairs. The substance and its conjugate is always opposite of each other. So two substances that differ from each other by a proton are a conjugate. So in this particular case, NH4 plus was the conjugate acid of the base NH3, and OH minus was the conjugate base of the acid or thing acting like an acid, in this case H2O. So when you look at them as their pairs, notice they are opposite each other if you've done it right. Now, this brings up something odd by Bronsted-Lowry definition. Sometimes water is acting like an acid, sometimes it's acting like a base. It seems like water can act like either. Well, substances that do that by Bronsted-Lowry definition are referred to as amphoteric, a substance that can act as either an acid or a base. In this particular situation, you can see that in the first case, since water is becoming an OH minus, it's losing a proton. So here it's acting like an acid. And that hydrogen ion is going to that substance when that becomes that. So this is acting like a base. Well, in the next reaction, HF becomes F minus. So this hydrogen is going to there. So now this is acting like an acid, and water is acting like a base. Water is amphoteric because with some things it acts like an acid, and with some things it acts like a base. And remember, I'm not saying water is an acid or base. When you think of the general term acid or base, what you're thinking of is when you throw something in water, what does it do to the water? Acids make water acidic, bases make water basic. That's different than what we're talking about. Now, the last idea I want to get into in the first set of notes here actually comes in section 19.3, the concept of strong versus weak acids and bases. A strong acid or a base is an acid or base that ionizes completely. It 100% breaks apart into its component ions. So this means that they are converted 100% to products, and they're represented by a single arrow when you write the reaction. So this would be an example of a strong acid. That single arrow means the HCl breaks apart 100% to H3O plus and Cl minus. And a strong base does the same thing. Single arrow, it 100% breaks apart into those two ions. So single arrow, 100% ionized, strong. Look for the single arrow when you see a reaction if you want to see if it's strong or weak. And in the case of weak acids or bases, they partially ionize. So they're equilibrium reactions, so they're reversible. So the products go back and make the reactants, so they don't stay products. You end up with products and reactants. So weak acids and base reactions, you can see they have double arrows. Now the last thing I want to look at is the concept of strong versus weak and concentrated versus dilute. They're not the same thing. Concentrated means you have a lot. So the two on the left are concentrated, the two on the right are dilute. Strong versus weak is, do you 100% break apart? This one, 100% is broken apart, and this one has 100% broken apart. The other two that I haven't boxed in the upper left-hand corner and the lower right-hand corner, those are weaks. They've only partially ionized. So concentrated versus dilute is a different idea than strong versus weak. So the top left is a concentrated weak acid. The top right would be a dilute strong acid. The bottom left would be a concentrated strong, and the bottom right would be a dilute weak acid. And that ends our first set of notes over chapter 19.